We're living in this time where most of the matter is dark. We're not actually seeing it. And most of what we call the energy density of the universe appears to be dark as well. So we're in what I like to call this period of maximum ignorance right now, where we've learned a ton about all of the normal matter of the universe, everything that makes you and the earth and the sun. But what we know today is that's only less than 5% of the universe. And then the other 95%, we don't know.
The majority of that 95% is dark energy, a mysterious force that's expanding the universe faster and faster. Cosmologists from around the world are unsure why this acceleration is happening. That's why, in the absence of data, an international team of scientists and engineers are building a dark energy hunting machine to probe the far reaches of the universe to a point in space-time few have ever seen.
So we call it dark energy because we don't know what it is. We can detect it through other measurements, but we can't observe it directly.
Scientists first became aware of dark energy in the late 1990s, after two independent teams of astrophysicists were racing to determine the rate at which the universe was expanding. Both teams expected to see the expansion slowing down due to the long-established theory that the attractive force of gravity was pulling the universe together. However, they observed something completely unexpected. The expansion of the cosmos was speeding up, not slowing down, meaning that there must be something like the appearance of an anti-gravitational force at play.
So we looked at that and it's like, oh yeah, that's weird. That can't possibly be right. They must have done something wrong. So it seemed pretty easy to dismiss it at the time.
But with further experiments and observations, the initial findings continued to hold up.
In fact, those original papers from 1998 and 1999, they knew what they were doing. They got it exactly right.
This repulsive force, which we now call dark energy, is something that still perplexes us.
It's easier to say what we do know about dark energy than what we don't know. So what we do know is that in the early universe, it was not very important. But at some point between 6 or 7 and 8 billion years after the Big Bang until today, dark energy became the dominant force affecting what's happening to the universe as a whole. We know it's not a particle because if it were caused by some particle, there would be other manifestations of it. So it appears to be something like a force, and at the moment, it's a very data-starved discussion. Every week, it seems, there are new theories coming out. So some of them having to do with this modification of our laws of gravity, some having to do with introducing new forces in the universe that would be a dark energy force or forces. And then there are other even grander ideas about additional dimensions in the universe effectively leaking in on the four-dimensional space that we see and exerting this force on our space. One of the first next big experiments to really measure this at this precision level is the DESI experiment.
DESI is a fiber optic spectrograph that will construct a 3D map of the universe, tracing close to 12 billion years of cosmic history. This engineering marvel is being mounted onto a telescope in Arizona, where it will measure the spectra of more than 35 million galaxies to observe dark energy's effect on a much grander scale.
We're using new classes of optical designs to get these large fields of view, and a big part of the DESI project was making this beast that we call the optical corrector. So it's really glasses on the top of the telescope. So it's a set of 6 lenses where the largest lens is 1.1 meters in diameter. And all of these lenses are polished to precision. Okay, so check, we've done that, big field of view.
The next challenge was figuring out how to catch the light of multiple galaxies at the same time.
We have a lot more fibers. We have 5,000 fibers. And we also have a really quickly reconfigurable focal plane. Each robot can move individually, so we can reposition every single fiber at the same time. So we cut down the time between observations from a few hours down to 3 minutes.
Which means with each fiber aimed at the sky,
we can map 5,000 galaxies every 15 minutes.
The main goal of the fiber system is to preserve the quality of light that the telescope delivers. You know, these photons have spent billions of years reaching us. We do everything possible within that fiber system to deliver the light to the spectrograph without degrading it. The spectrograph is 10 identical units that fill an entire room.
DESI is nearing completion of its installation phase and gearing up to scan the skies.
We have the focal plane installed, and then after the focal plane is safe to operate, then we install the fiber cables to the slits.
We'll make a precision map of the geometry of the universe from a distance of about 7 billion light years to about 10 or 11 billion light years. And so this is the phase of history of the universe where dark energy kind of turned on, where it became the dominant force in the universe.
So, to construct a 3D map and understand dark energy's role, DESI will first need to look at a unique cosmological effect.
The universe did deliver a specific feature that we can latch onto, and that's this baryon acoustic oscillation feature. When the universe went through this specific transition where it was a plasma of very hot ions and then cooled off as it was 383,000 years after the Big Bang. Right at that time, there were sound waves propagating in the universe that got frozen in.
Mapping those sound waves with DESI will give scientists a sense of the distribution of the galaxies and scale of the universe. But BAOs don't give us the whole picture. In this age of accelerated expansion, galaxies are moving away from us, so scientists need to measure how fast they're traveling. Fortunately, galaxies leave a clue behind. They're light waves. These waves are stretched to redder and redder wavelengths, which is called their redshift. By knowing a galaxy's redshift, scientists can tell how far away it is and turn our view of the sky into a 3D map.
On the first year of operations, starting in 2020, we'll actually have a larger map of the universe than all of humanity before us. So we'll be able to verify what our understanding of dark energy is today, geometry at a few different epochs, how dark matter is pushing around these galaxies. That's what we'll see after the first year. And then it'll be the subsequent years where we'll have a large enough map that it'll really be the new discovery potential for dark energy.
These cosmic map makers are charting the open sky, uncertain of what they'll eventually find. But diving into the unknown is just part of the job. What they learn in the end will only expand our knowledge of the universe and our small place in it.
The better we understand dark energy, the better we understand how the universe is going to evolve, and we learn what's going to happen to the universe in the end.
What I can tell you is that these will be the best data that we have once we complete this map, and it will certainly rule out many, many potential models for dark energy, and it'll be very interesting to see what's left on the table after that.